Imagine a force powerful enough to shape entire galaxies, yet so deeply hidden that even light struggles to escape, and time itself begins to distort. At the center of countless galaxies, including our own, this force waits, a supermassive black hole. Long thought to be nothing more than a cosmic predator, it now reveals a far more unsettling role. These objects do not simply consume matter, they reach outward, reshaping their surroundings, triggering the birth of stars, steering the evolution of galaxies, and quietly influencing the long chain of events that eventually allows planets like Earth to exist. As we begin to understand how deep this influence runs, the universe no longer feels stable. The picture we trusted starts to crack. To understand this shift, we are drawn to quasars, the blazing hearts of active galaxies. Fueled by supermassive black holes devouring immense amounts of matter, quasars can outshine every star in their host galaxy combined. But among them, one group stands apart. Red quasars appear shrouded, buried beneath thick clouds of cosmic dust. Their color is not a coincidence. Dust absorbs blue light and lets red wavelengths pass, muting their glow while intensifying their radio emissions. Observations from DESI and LOFAR confirm this behavior. Research led by Victoria Fawcett at Newcastle University reveals that red quasars produce stronger radio signals than their clearer blue counterparts. Powerful radiation slams into surrounding dust, violently stirring its molecules and forcing them to release radio waves. In this chaos, red quasars become impossible to ignore, broadcasting their presence across the universe. Their importance runs deeper than their signals. Red quasars appear to belong to an earlier, more chaotic stage of galactic life. The dust that obscures them is not random debris, it is a leftover scar, likely forged during a starburst phase triggered by galaxy mergers or other disruptive encounters. As the central black hole continues to feed, its energy gradually tears this dusty shroud apart. What emerges is a blue quasar, cleaner, more exposed, and quieter in radio emission. This transition, known as the blowout phase, marks a profound shift from a dust-choked, radio-loud state to a clearer, more subdued one. By observing red quasars, astronomers are witnessing the opening moments of this transformation. The identification of thousands of these objects reveals that they are not rare curiosities, but essential fragments of a larger, unsettling pattern. As supermassive black holes grow, their galaxies are reshaped alongside them, bound together in a restless and unstable evolution. With this foundation in place, the blowout phase comes into sharper focus. This phase represents a critical turning point in young, active galaxies, when the supermassive black hole begins to expel the dense gas and dust that conceal it. The theory traces this moment to the immense forces generated within the accretion disk. As matter spirals inward, gravitational stress creates extreme friction, heating gas and dust to millions of degrees. This process not only ignites the quasar's brilliance, but also builds toward violent releases of energy. These releases drive the clearing of the surrounding material and usher in the blowout phase, a moment when concealment gives way to exposure and the galaxy itself is irrevocably changed. These streams of high-speed winds and magnetically collimated jets move like ruthless space brooms, sweeping away dust and gas. As they collide with surrounding matter, the jets generate shock waves that intensify the cleansing over time. Layer by layer, the shroud thins, the quasar interior emerges, dust fades, and the quasar begins to shine more fiercely in optical and ultraviolet light, the stage already identified as the blue quasar. Observations from space telescopes support this unsettling picture. With its infrared vision, JWST peers through the dust and exposes the inner dynamics of this violent phase. What appears is not calm structure, but interaction. Jets batter surrounding matter, driving dust and gas out from the galactic nucleus. The evidence aligns disturbingly well with predictions of the explosion phase theory, leaving little room to doubt that red quasars exist in a fragile state of transition. And then, the news itself arrives. Again. The James Webb Space Telescope opens yet another fracture in our understanding of the cosmos. Among its revelations, the galaxy ESO 428 G14 demands attention. Roughly 70 million light-years away, it hosts an active galactic nucleus where a supermassive black hole exerts overwhelming influence on nearby space. This is no ordinary galaxy. Its nucleus floods the electromagnetic spectrum with radiation as the black hole consumes matter at an extreme rate. The energy released rivals the brightest objects known. Yet what unsettles astronomers is not the brightness, but the shock features and swirling clouds of dust and gas encircling the black hole. Something is happening here that does not fit comfortably with old expectations. For a long time, the dominant idea held that dust surrounding an active galactic nucleus was heated directly by radiation from the black hole. JWST revealed something far more disturbing. The heat does not come only from radiation, but also from violent encounters with jets of gas launched from the black hole poles at speeds approaching light itself. These jets slam into surrounding matter, creating shocks. Their impact rewrites the narrative. Scientists once argued over how active galactic nuclei transfer energy outward. The realization that radio jets can so thoroughly disrupt nearby dust and gas was not anticipated. Assumptions fracture, and new questions surface about the behavior of supermassive black holes. The consequences ripple outward. By tracing how radio jets interact with surrounding matter, JWST sharpens our view of how supermassive black holes shape not only their immediate environment, but the entire galaxy. Jets, once dismissed as secondary effects, now appear central, influencing star formation and the very structure of the galaxy. This phase is not optional. It is a critical component in the uneasy relationship between black holes and their hosts. To grasp this influence, attention turns to feedback mechanisms governing these interactions. At the heart of many galaxies lies a supermassive black hole wrapped in a turbulent region known as an active galactic nucleus. This environment radiates intensely, driven by an accretion disk of gas and dust spiraling inward. Heated by immense gravity, the disk emits across the electromagnetic spectrum, from X-rays to radio waves. It is not uniform. Conditions shift dramatically with distance from the black hole. In the inner regions, matter races inward, generating extreme heat and high-energy radiation. Now, even the outer edges of these disks refuse to remain hidden. Recent observations have exposed them for the first time. Using the James Webb Space Telescope and the Gemini Near-Infrared Spectrograph, researchers detected emission lines from the distant quasar 3Z2. Stretched by the Doppler effect, these lines reveal the immense size of the accretion disk and the turbulence within it. The light arises as atoms absorb energy, become excited, then fall back to lower states. The double-peaked profile, shaped by disk rotation, allows astronomers to measure the disk itself. What emerges is not reassurance, but clarity. Matter under the grip of a supermassive black hole behaves in ways that quietly undermine any sense of stability we once assumed. But the accretion disk is not the only presence on this stage. From its poles erupt radio jets, torrents of charged particles hurled to near light speed by the black hole's magnetic grip. These jets are not incidental. They strike the surrounding dust and gas with violent force, driving shock waves that can reshape an entire galaxy. In some regions, they ignite star formation. In others, they suffocate it. This uneasy exchange, known as AGN feedback, governs how galaxies grow, enriching nearby gas with heavy elements or sweeping it away entirely. Through these jets, the balance between star birth and star death is quietly dictated. Jets are not the only reach of a black hole's influence. There are tidal disruption events, moments when a star wanders too close and is torn apart by gravity. The star is stretched and shredded, its matter divided between what falls inward and what is flung outward. Recent findings show that much of this stellar material escapes, forming a vast spherical cloud of gas that can block high-energy radiation, such as X-rays. Seen through polarized light, this cloud reveals the aftermath of a feeding black hole, a lingering scar left on its surroundings. Yet this obscuring matter is not meaningless debris. Cosmic dust holds clues to how the universe works. Often dismissed as residue, it is built from the remains of stars, made of microscopic grains of carbon, silicon, and metals. These particles are born in supernova explosions, when dying stars scatter their outer layers, and in the slow shedding of red giants near the end of their lives, dust marks the cycles of stellar life. It drifts, cools, and is folded back into new stars, planets, and eventually life itself, a quiet system of cosmic recycling. At the same time, this dust distorts what we think we see. It scatters and absorbs light, especially in the visible range, veiling galactic centers and active nuclei. Black holes and quasars can vanish behind it, their most telling features concealed. Infrared observation changes this fragile picture. By sensing heat and longer wavelengths, the James Webb Space Telescope peers through the haze, revealing what lies within and behind these clouds. The view ahead grows wider still. The Nancy Grace Roman Space Telescope, launching in 2027, will survey immense swaths of the infrared sky, capturing images far larger than Hubble ever could while preserving fine detail. With this flood of data, billions of galaxies come into focus, and a three-dimensional map of the universe begins to emerge, even as the ground beneath our understanding continues to feel uncertain. This telescope promises more than sharper images of cosmic dust and how galaxies take shape. It hints at answers to questions that once felt untouchable. Dark energy, the large-scale structure of the universe. As we map cosmic expansion or uncover distant exoplanets, the future of space exploration opens into something vast and unsettling. Revolutionary technologies are already pushing us toward truths that may permanently fracture how we understand the cosmos. Curiosity pulls us upward, yet the sky no longer feels reassuring. The universe is crowded with mysteries, and not all of them feel welcoming. At some point in our lives, most of us have wondered whether we are alone. With countless planets circling innumerable stars in our galaxy and beyond, the silence begins to feel strange. Why have we found no trace of extraterrestrial life? And what if advanced civilizations have existed for ages, unseen, not absent, but concealed? The dark forest hypothesis suggests that technologically advanced societies may already thrive beyond our solar system, choosing silence not out of weakness, but fear. Fear of being attacked, or perhaps the cold calculation of preparing to strike first. Today, you confront the dark forest theory and the unsettling idea that being noticed in the vast cosmos may be the most dangerous outcome of all. The dark forest hypothesis traces back to science fiction writer Lou Sagan. It is not a scientific theory and rests on no empirical evidence. In 2008, L. Sagan published his novel titled The Dark Forest, where the idea was first articulated. At its core lies a bleak assumption. Every civilization, on a cosmic scale, seeks resources to survive. To endure, extraterrestrial life must remain hidden, avoiding destruction, while quietly preserving the option to destroy others if necessary. The name emerges from a metaphor. The universe becomes a dark forest filled with hunters. Each civilization is an armed figure moving silently, terrified of being seen. Discovery is not an invitation, it is a trigger. If one hunter finds another, survival demands striking first. From this emerge several grim principles. Alien civilizations may exist, but remain concealed to avoid annihilation and the loss of hard-won resources like inhabited worlds. Survival becomes entangled in what the hypothesis calls a chain of suspicion. Limited communication breeds mistrust, and mistrust hardens into preemptive hostility. Cooperation is nearly non-existent, as expansion and survival outweigh all else. Alliances might occur, but only when mutual benefit is undeniable and temporary. In this vision, the universe resembles a battlefield of scarcity, where trust is a liability. Only highly advanced civilizations matter in this forest. Those too weak to announce themselves drift unseen, or worse, become easy prey. The dark forest hypothesis also serves as a response to the Fermi paradox. In 1950, physicist Enrio Fy famously asked, Where is everyone? If the galaxy formed millions of years before humanity, then other civilizations could have arisen long before us. Older, more advanced, and yet the silence persists. Within the dark forest, that silence no longer feels empty, it feels intentional. Therefore, the Milky Way should be crowded with civilizations capable of detecting our signals and even crossing the galaxy with technologies far beyond ours. Yet nothing appears, no visits, no traces, no unmistakable signs of alien activity. The question hangs unresolved. Why has no one come close enough to notice us? To estimate how many extraterrestrial civilizations might exist, the Drake equation was proposed in 1961, but it cannot explain the silence. It cannot tell us why no evidence has ever been left behind. For now, the Fermi paradox remains trapped in theory. According to physics professor Adam Frank, the chance that humanity is the only civilization in the universe is vanishingly small, 1 in 10 billion trillion, a number so large it almost dissolves meaning. Our evolution, he argues, was not unique. Other civilizations could have emerged long before us, perhaps surviving for far longer. More than 70 hypothetical answers attempt to explain this contradiction. One of them is the dark forest hypothesis. We cannot verify it with our current technology. Still, Liu's theory offers a disturbing logic for the cosmic silence. Revealing one's location is dangerous. Any signal could invite destruction. Yet even this idea fractures under closer inspection. If civilizations exist, they would not all stand at the same stage of development. Different origins imply different capabilities. As Frank pointed out, some societies could match or exceed our level and still search for life openly, studying their surroundings without fear. Conflict is not inevitable if confrontation has never occurred. We may not be alone in transmitting signals into the void. Many assumptions of the dark forest hypothesis mirror human history. The vision of cosmic conquest recalls colonization and war on Earth. Empires expanded for power, land, and resources. In the 19th century, European industrial growth demanded materials found elsewhere. Africa supplied them, at enormous cost to its land and people. Development on one side was built on devastation on the other. The dark forest applies the same colonial logic to the universe. Humanity itself still pursues expansion. We study exoplanets, map distant systems, and plan to settle Mars. The red planet holds resources essential for technological progress. If another civilization seeks the same necessities, competition becomes imaginable. Survival, in this view, depends on securing limited resources. Without them, extinction looms. Beyond scarcity, the hypothesis introduces another source of danger: the chain of suspicion. Civilizations cannot know whether others are peaceful or hostile. Uncertainty breeds fear. Fear invites preemptive action disguised as self-defense. Researcher Chiao argues that such a chain emerges only between societies of comparable technological power, where each side can realistically judge the other's capabilities. In that balance of doubt, silence may feel safer than existence itself. Thus, if a significant gap exists in levels of development, the chain cannot hold. A technological explosion refers to the ability of cosmic civilizations to leap forward suddenly, and such a rise turns a new hunter into a threat. Advanced civilizations may grow wary or decide to erase it. Yet Chow notes that an invasion is never clean. The attacker exposes itself. Other civilizations, equally advanced or more so, could detect the act, tightening the chain of suspicion. Even power breeds fear. Despite the apparent advantage of attack and stealth, the dark forest hypothesis considers another path: benevolence. To refuse to strike even when others are detected, to answer signals in the dark. This choice is perilous. A benevolent civilization may face one that turns hostile or evolves rapidly, gathers resources, and survives by destroying others. Benevolence, in contrast, likely fades. If extraterrestrial life truly exists and is far more advanced than us, then attacking Earth may appear as the strategy with the highest chance of survival. That realization is unsettling. So the question remains, Are there outcomes that spare Earth under the dark forest hypothesis? Game theory offers a lens. Imagine Earth as Civilization A and a more advanced alien society as Civilization B. B detects our radio signal and faces three options: attack, remain hidden while growing suspicious, or respond with the possibility of friendship. Attack seems optimal, even if A can resist. Yet this path may collapse if A can transmit B's coordinates to other civilizations. In that case, secrecy becomes safer. If both remain silent, neither gains resources, but both avoid destruction. Friendship is also possible. An alliance could grant A access to alien technology, while B gains something in return, though less. This seems ideal, but it fractures under scrutiny. Benevolence is dangerous. Friendly civilizations may be rare. The resources gained through cooperation are fewer than those seized by force. Thus, an attack on Earth appears statistically dominant. Still, it is not without cost. Fear of Earth's unknown potential may push others towards secrecy or cautious contact. This leads to a deeper unease. If conquest is more likely than peace, should we fear our own signals? The dark forest hypothesis suggests yes. Broadcasting our presence may threaten our survival. Many astrophysicists share this concern, including Stephen Hawking. Since the mid-20th century, humanity has actively searched for extraterrestrial intelligence. In 1974, the Arecibo message was sent toward a star cluster 21,000 light-years away. Since then, multiple signals have followed, the most recent in 2017. Hawking warned that such messages could invite the very outcome the dark forest predicts. An alien arrival, he argued, might mirror what colonization brought to the indigenous peoples of the Americas. Not discovery, but collapse. Therefore, he concluded that this form of communication should be halted. Yet other scientists, including SETI astrobiologist Douglas Bako, warned that fear of sending messages could push Earth into isolation. Vach also noted an unsettling truth. If hostile alien civilizations existed, they would have had ample opportunity to destroy our planet when it was still fragile and forming. From this perspective, the fear of being heard begins to feel misplaced. Even the dark forest hypothesis itself implies variation in predatory behavior, suggesting that not every civilization would instinctively attack upon detection. A group of independent researchers led by the Global Catastrophic Risk Institute and Seth Baum went further, proposing that alongside potentially dangerous civilizations, there may also be those with limited capacity for harm. Some might remain silent by choice, preferring concealment over contact. Others might even seek cooperation, capable of forming peaceful relationships and helping humanity confront global crises. The dark forest hypothesis, then, is not a definitive answer to the haunting question of where everyone is. Other explanations persist, from the vast distances separating civilizations to the sheer improbability of life arising elsewhere. L. Shin's theory cannot be dismissed outright, yet neither can it be confirmed, leaving us suspended between suspicion and uncertainty. Approximately 13.8 billion years ago, a singularity of infinite density and gravity emerged, rapidly expanding and cooling to give rise to our universe. We call this event the Big Bang, but this explanation settles nothing. It only deepens the unease. What existed before the Big Bang, if the concept of before even applies to a universe where time itself was born in that eruption? Are we merely one fleeting phase in a relentless cycle of cosmic death and renewal? The greatest minds of our species have proposed visions as unsettling as they are profound. Some speak of other universes, others imagine a cosmos that breathes, expanding and collapsing endlessly. In trying to understand what came before time, we confront how unstable our assumptions truly are. Consider a universe that inhales and exhales. It expands from a single point, grows for billions of years, then reverses, drawing everything back inward. This is the essence of the oscillating universe theory. In this view, our universe is not unique, but a temporary phase in an eternal rhythm of expansion and contraction. Each cycle begins with a Big Bang, followed by eons of growth, until expansion slows, halts, and collapses into contraction. This contraction culminates in the Big Crunch, where galaxies collide, stars are crushed, and all matter and energy are compressed into a singularity nearly indistinguishable from the one that began it all. Yet even this is not an ending. The singularity erupts again, igniting another Big Bang and another universe. Each cosmic lifespan may last billions or even trillions of years, each collapse preparing the conditions for the next creation. It feels less like a universe with purpose and more like a pendulum, swinging endlessly, erasing and rebuilding reality without memory or intent. Still, the oscillating universe remains deeply uncertain. We do not yet understand the true nature of cosmic expansion, the precise makeup of the universe's energy, or how gravity behaves on such unimaginable scales. Observations of the cosmic microwave background suggest an expansion that is accelerating, not slowing toward collapse. The universe may not be preparing to return inward at all, and yet, science has a way of resurrecting discarded ideas when new evidence appears. As our exploration of space and time continues, one belief quietly fractures. We once thought our universe was singular, a lone bubble drifting in infinite emptiness. But what if it is not? What if our universe is only one among countless others, indistinguishable, unreachable, and utterly indifferent to our search for certainty, each with its own laws of physics, its own history, its own beginning and end? This is the premise of the multiverse theory. I try to picture it as a vast cosmic ocean where countless bubbles form and vanish. Each bubble is an independent universe, and ours is only one fragile pocket within this restless foam. Some of these universes may be radically different, shaped by other physical constants or extra dimensions. Others might be disturbingly similar, perhaps even hosting life much like ours. And a more unsettling thought follows. What if some of them came before us? What if our Big Bang was not an absolute beginning, but the result of an encounter with another universe? The multiverse idea erodes any comfort we might have about our place in the cosmos. It is captivating, yet deeply controversial. If these other universes lie forever beyond observation, how could we ever study them? And if a theory cannot be tested, can it still belong to science? Despite these doubts, the multiverse remains an active subject of research and dispute. It marks the frontier where physics begins to blur into philosophy, where observable facts thin out and hard questions about the nature of reality take their place. Yet even as this vision multiplies universes beyond counting, we are forced back to the uneasy foundations of our own. Our understanding rests on two pillars of modern physics. Quantum mechanics governs the atomic and subatomic realm. General relativity governs the vast structure of space and time. Each works with extraordinary precision, yet they speak incompatible languages. And the moment they are forced together, the ground begins to crack. According to general relativity, space and time are woven into a four-dimensional fabric known as space-time. Massive objects bend this fabric, and we experience that distortion as gravity. Quantum mechanics, in contrast, describes a world where particles exist in multiple states at once, flicker into and out of existence, and defy everyday logic. These two frameworks collide at the Big Bang and at the cores of black holes, where gravity and quantum effects are equally extreme. For decades, physicists have searched for a theory of quantum gravity to reconcile this fracture. One proposal to emerge from this struggle is the no-boundary idea, developed by Stephen Hawking and James Hartle. In this view, the universe did not erupt from a singular point of infinite density. Space and time are finite, yet without edges. Like the surface of the Earth, you can travel indefinitely without ever falling off. In this model, the universe resembles a four-dimensional sphere, and the Big Bang becomes a smooth point, comparable to the North Pole, special but not singular. Asking what came before the Big Bang loses meaning, just as asking what lies north of the North Pole leads nowhere. It is an elegant way to sidestep the singularity, though it remains contested and incomplete. Still, it gestures toward a possible reconciliation between the infinitely large and the infinitely small. Pushing even further, string theory offers a more radical shift. In this framework, the fundamental constituents of reality are not point particles, but one-dimensional strings. Their vibrations give rise to all known particles: electrons, quarks, photons, each a different note in a deeper cosmic resonance. Yet string theory does not confine itself to the dimensions we know. It implies the existence of additional spatial dimensions, hidden or compact, silently shaping the structure of reality. Within this context, a variant known as the pre-Big Bang scenario, or the ekpyrotic model, suggests something even more destabilizing. Our universe may have been born from a catastrophic collision between two vast higher-dimensional worlds, leaving us inside the aftermath, still trying to understand what shattered to make our beginning possible. After such a collision, the two brains recoil, drift apart, then slowly fall back under gravity, only to collide again billions of years later, perhaps igniting another universe. If so, what existed before the Big Bang? In this picture, it may have been another universe much like ours, living on a brain parallel to our own. Yet string theory, for all its elegance and its promise of uniting quantum mechanics with gravity, offers no empirical proof. We already know how elusive such verification is, so doubt creeps in. What if the problem is not what came before our universe, but how we imagine nothingness itself? When we think of a vacuum, we picture absolute emptiness. Quantum mechanics refuses this comfort. The vacuum is restless, a seething ocean where particles and antiparticles briefly appear and erase each other. These vacuum fluctuations suggest another unsettling idea. Our universe may have begun as one such fluctuation. A minute bubble of false vacuum could have swelled into everything we see, driven by quantum rules rather than intention. Through phase transition or quantum tunneling, the bubble would expand violently, its boundary pushed outward by negative pressure. The energy trapped inside could condense into matter, becoming stars, galaxies, and eventually us. In this view, before the Big Bang there was only a quantum vacuum, crowded with fleeting particles, and our universe was a single random bubble that happened to survive and grow. This idea is seductive, but it fractures certainty. Why did this bubble expand while countless others faded? How can an eternal quantum vacuum coexist with a universe that seems to have an age? Each answer opens more unease, and as quantum physics deepens, it hints at further possibilities, leading to another disturbing vision, the Big Bounce theory. Imagine a universe that expands, collapses, then rebounds. Instead of dying in a singularity where physics dissolves, the universe shrinks to a tiny scale and, through quantum effects, begins expanding again, what we perceive as the Big Bang. Like other cyclic models, it suggests no true beginning or end, only endless renewal. What sets the Big Bounce apart is its focus on the instant of reversal, the fragile moment between collapse and expansion. Here, quantum mechanics is invoked again. On the smallest scales, particles can tunnel through barriers they should not cross. Some theories suggest the universe itself could tunnel from contraction into expansion. Yet this remains deeply speculative. Evidence of a prior contraction is absent. A complete quantum theory of gravity is still out of reach. The mechanism that allows a shrinking universe to recover without breaking known physics remains unclear. Time and causality themselves feel strained, and so uncertainty persists, pushing us toward other unsettling ideas, such as the possibility that our universe emerged from something we already know, yet barely comprehend, a black hole, vast, consuming, and perhaps creative. They are regions of space where gravity becomes so overwhelming that nothing, not even light, can escape. At the heart of a black hole, general relativity predicts a singularity, a point where density diverges and space-time bends beyond comprehension. Yet what if this is not an ending, but a threshold? Some physicists quietly suggest that the singularity inside a black hole could ignite a new expanding universe. In that unsettling picture, our universe itself might be the interior of a black hole nested within a larger parent universe. The Big Bang would then align with the moment that black hole formed, and cosmic expansion would mirror the black hole's internal growth. The question of what came before the Big Bang no longer points to nothingness, but to the interior of another universe. Perhaps every black hole carries the potential to generate a universe within itself. Still, this remains a hypothesis, fragile and unresolved. How could such an idea ever be tested? Could traces of a parent universe be observed? And how does this fit with what we think we know about black holes and singularities? Loop quantum gravity enters this uncertainty as an attempt to reconcile quantum mechanics, which governs the smallest scales, with general relativity, which governs the largest. It suggests that space is not smooth and continuous, but built from tiny, indivisible loops. When this framework is applied to the cosmos, in what is called loop quantum cosmology, it points toward a rebound rather than a breakdown. Instead of collapsing into a singularity as classical relativity demands, the universe contracts to a minimum size where quantum gravitational effects intensify and reverse the collapse. Expansion follows. In this view, the universe may have passed through repeated cycles of contraction and expansion, each beginning with a quantum jump. The mystery of what existed before the Big Bang shifts again. It may have been a prior phase of the same universe, a contraction that ended in a quantum transition. Within loop quantum cosmology, the notion of a quantum bridge emerges. There is no singularity. Instead, there is a leap, a transformation where contraction gives way to expansion. This bridge is not a structure one could traverse, but a fleeting phase in cosmic evolution governed by quantum gravity. Beyond the Big Bang, the previous universe is not erased, but connected to ours through this transition. Even so, the theory carries serious challenges and unanswered questions. Yet if it holds, it sketches a deeply unsettling vision. A universe without a true beginning or end, endlessly cycling through collapse, quantum jumps, and rebirth. Intriguing, fragile, and far from settled, these ideas leave the sense that the ground beneath our understanding is far less stable than it once appeared. They remain in the realm of speculation. Each carries its own strengths and its own weaknesses, and none has yet been backed by conclusive experimental evidence. Even as we move closer to answering what came before the Big Bang, it becomes clear that every answer fractures into further questions. This is where the unease sets in. Science advances not by certainty, but by probing the unknown. Researchers across the world continue to refine these theories, knowing that even partial progress reshapes the wider picture. So, in simple terms, what happened before the Big Bang remains uncertain. We do not know, yet the pursuit itself deepens our understanding and compels us to keep looking outward into a universe that refuses to settle into fixed answers. Across the vastness of space, among innumerable stars and galaxies, there is a whisper that has traveled for years to reach Earth. This is not fiction, it is a real trace of the universe speaking softly. Scientists listening to space have detected a radio signal, a faint wave arriving from a star system not unlike our own. The star, YZ Ceti, lies just 12 light-years away. What unsettles us is not merely the signal's existence, but what it suggests. The signal appears to carry the imprint of a magnetic field, strikingly similar to the one that shields Earth. Such a field could surround a rocky, Earth-sized exoplanet orbiting YZ Ceti. The implication lingers. Could this distant world resemble our own more closely than we once believed? And what does that possibility mean for the search for life beyond our solar system? These questions pull us across light years toward the quiet mystery of radio signals and the invisible shields of distant worlds. In the boundless silence of space, radio signals are rightly called whispers. They are a form of electromagnetic radiation, no different in nature from light, X-rays, or microwaves. They arise from stars, galaxies, and human-made spacecraft alike. Traveling at the speed of light, they carry information across distances that strain comprehension. Within them lie clues about stellar composition, the presence of planets, and even the origins of the universe. Detecting them depends on radio astronomy. Instruments like the Very Large Array in New Mexico and the former Arecibo Observatory in Puerto Rico act as our ears, tuned to the faintest murmurs of the cosmos. Once captured, these signals are examined through complex algorithms and models, revealing details about their source, its location, its distance, and its physical nature. Yet these whispers are not only abstract curiosities. They underpin modern life through satellite communication, navigation, weather forecasting, and observation of Earth itself. When you look at the night sky, there is more than darkness above. There is a continuous, unseen conversation, a cosmic orchestra we are only beginning to hear. Return now to the constellation Cetus, the sea monster, where a star continues to whisper across the void. YZ Ceti is a red dwarf, smaller and cooler than the Sun, a nearby neighbor on a cosmic scale. What draws attention is not the star alone, but what circles it. At least 3 exoplanets orbit YZ Ceti. The innermost, YZ Ceti b, stands out. It is a rocky, Earth-sized world orbiting extremely close to its star. So close that its year lasts only 1.6 Earth days. Recently, using the Very Large Array, scientists at Bucknell University detected a repeating radio signal from this system. Recorded between 2 and 4 gigahertz, the signal appears shaped by the star's rotation and the orbit of YZ Ceti b. This points to an interaction between the star and the planet's magnetic field. The finding unsettles old assumptions. While YZ Ceti b itself is unlikely to host life due to its harsh proximity to its star, the detection of its magnetic field matters. It hints at a way to identify more hospitable worlds elsewhere. Still, the meaning of this signal is not settled. Why magnetic fields matter, and what they truly reveal about life beyond Earth, remains an open question, one that refuses to close neatly. We have to look past what we can see into the unseen fields that quietly shape the universe. Magnetic fields are a fundamental force, steady yet elusive. They guide compasses, steer migrating birds, and shield our planet from the relentless solar wind. But they do not belong to Earth alone. Beyond our world, they are everywhere, woven into the larger structure of space. The Sun carries a magnetic field that is complex and unstable, governing its behavior from sunspots to violent solar flares. On even larger scales, magnetic fields shape galaxies, guiding interstellar gas and influencing how new stars come into being. What unsettles the mind most is their role in planetary habitability. A strong magnetic field can stand between a planet and its star, preserving an atmosphere and perhaps the fragile conditions needed for life. This is why the possible detection of a magnetic field on exoplanet YZ Cb matters so much. It hints at an atmosphere that might endure, at a world that has not yet been stripped bare. Yet magnetic fields also complicate how we see the universe. Radio signals, themselves made of intertwined electric and magnetic oscillations, do not travel untouched through space. As they pass through magnetic fields, they bend, their polarization twists, their frequencies shift. Each distortion carries information, clues about the strength and orientation of the field encountered. By reading these subtle changes, scientists can infer properties of distant magnetic environments. At the same time, these same effects can obscure what we are trying to detect. Signals can interfere with one another, become warped, and lose clarity. This is why magnetic fields sit at the heart of radio astronomy. Only by understanding how they deform radio waves can we correct for their influence and recover what is hidden in the noise. To grasp what this means for life, it helps to look closer, toward Mars, our familiar red-headed neighbor. The red planet fascinates with its immense volcanoes, vast canyons, and traces of ancient water. But beneath this grandeur lies a troubling absence. Unlike Earth, Mars has only a weak and uneven magnetic field. It is not powered by an active dynamo in its core, but by remnants locked into the crust from a distant past when a global field still existed. Without strong magnetic protection, the Martian atmosphere is exposed directly to the solar wind. New models suggest something even more unsettling. A weak magnetic field, like that of Mars after its dynamo shut down, may accelerate atmospheric loss rather than prevent it. Simulations show that such a field leads to the fastest rate of atmospheric ion escape, several times greater than if no magnetic field were present at all. The weakened field lines are easily pushed aside by the solar wind, opening pathways for ions to leak into space on the night side of the planet. Over billions of years, this quiet erosion transformed Mars. Its atmosphere thinned, a process known as atmospheric stripping, and a world that may once have been warmer and wetter collapsed into the cold, barren planet we see today. Mars stands as a stark reminder that magnetic fields are not just a detail of planetary physics. They can decide whether a world endures or slowly unravels. It reveals something unsettling. Without a strong magnetic field, a planet, even one that once resembled Earth like Mars, can slowly lose what made it livable. Atmosphere thins, water disappears, habitability slips away. That quiet collapse forces us to look outward. Exoplanets, worlds circling stars beyond our solar system, have become a central focus of astronomy. More than 1,000 are now known, each one hinting at how varied and fragile planetary systems in our galaxy can be. One moment in this search stood out. In late December 2021, an international team using the Hubble Space Telescope detected what appeared to be the first known magnetic field on an exoplanet. It was found on a Neptune-sized world called HAT P11b, roughly 123 light-years away in the constellation Cygnus. This planet is a hot Neptune, similar in size to Neptune, but pulled dangerously close to its star, its surface locked in extreme heat. The discovery felt like a crack in what we thought we understood. It suggested that exoplanets can generate magnetic fields, not unlike the planets we know, and that matters more than it first appears. Magnetic fields shape what survives. They hint at internal structure, at atmospheric behavior, at whether a planet can resist the erosion of stellar winds long enough to keep conditions stable. Without that shield, even promising worlds may quietly unravel. This brings us back to YZ Ceti b, an exoplanet from which a strange signal was recently detected. If that signal truly points to a magnetic field, it could change how we see this world and its potential for life. From the barren remains of Mars to the distant system of YZ Ceti, a pattern emerges. Invisible magnetic forces are not secondary details. They decide which planets endure. At the same time, the study of signals from deep space has accelerated. Instruments like the giant Metrovave radio telescope in India have captured faint emissions from the most distant galaxy yet observed. The signal linked to YZ Ceti opened another narrow window, reminding us how incomplete our picture still is. Looking ahead, listening to these distant signals will remain at the center of space research. Each one carries the weight of the unknown, so when we stare into the night sky, we are not only seeing stars and galaxies, we are facing a universe filled with unseen forces, whispered messages, and fragile possibilities. And as we keep listening, the next discovery may not confirm our certainty, but quietly undo it. Tonight, we followed a thread that started in the brightest places and led us into the quietest ones. From supermassive black holes shaping galaxies, to quasars blazing like exposed cores, and then to the red quasars that stay half hidden behind dust. Louder in radio because radiation crashes through their shrouds and forces the dust to answer back, as if the universe itself cannot keep a secret forever. We watch that dust become a phase, not just debris, a temporary veil in a larger transition where a young active galaxy moves through a blowout moment, when winds and magnetically guided jets begin to sweep the choking material away until a clearer, bluer quasar stands, revealed, changed, and changing its host in return. We let the James Webb Space Telescope widen the crack in our certainty, showing how jets can heat and shock surrounding dust and gas, not simply by light but by impact, and how that violence can rewrite what we thought powered the warmth around an active nucleus. From there, the story drifted outward into feedback, the uneasy balance where jets can ignite star formation in one region and suffocate it in another, and where even a torn star can leave behind a cloud that blocks high-energy light like a lingering bruise on space-time. We remembered that cosmic dust is both creator and curtain, born from dying stars and recycled into new ones, while also scattering and absorbing light so thoroughly that what we think we see is never the full truth, which is why infrared eyes like Webb and future surveys like the Nancy Grace Roman Space Telescope matter, because they promise to map wider swaths and bring billions of galaxies into focus, even as the ground of understanding still feels unsteady. Then the script turned, as if the universe itself had changed subject without warning, into the question of silence. The dark forest idea where a cosmos full of life might choose not to speak, because discovery could be a trigger and caution could look like emptiness, and where even our own signals start to feel like a candle in a forest that might prefer darkness. It carried us further back, to the Big Bang, and the uncomfortable fact that explaining an origin does not dissolve the mystery. It sharpens it, because the word before begins to fail when time is part of what began. And so the mind invents cycles, bounces, collisions, quantum bridges, and even the possibility that a black hole could be a threshold into another expanding reality. All of it hovering between mathematics and wonder, between elegance and doubt, and finally, we return to whispers, not metaphorical but literal, radio signals crossing space, carrying hints about their sources, and in one nearby system, YZ-SETI, a repeating radio signal that may point to an interaction with a planet-sized world and its magnetic field, a reminder that invisible shields matter, that they can preserve atmospheres, and that without them worlds can be stripped down to silence, as Mars was, slowly losing the conditions that once might have held water and warmth. Now, let all of that knowledge soften, as if you are letting it drift away from the sharp front of your mind and settle into the deeper, slower place where sleep begins, because you do not need to solve the universe tonight. You only need to rest inside it. Picture the night sky not as a vast problem to be answered, but as a ceiling of gentle distance, a slow ocean of dark velvet, where the brightest points are not demanding anything from you. They are simply there, steady, patient, older than urgency. Imagine a red quasar far away, wrapped in dust like a lantern behind a curtain, its radio voice traveling without effort, without strain, a long soft hum that does not rush. Imagine those jets, not as violence now, but as silent brushstrokes you can barely see, shaping clouds the way wind shapes fog, the way your breath shapes the quiet inside your chest, and with that image, begin to breathe, as if you are syncing with the universe's own slow rhythm. Inhale gently through the nose, unforced, feeling the air cool at the entrance, letting the chest rise just a little, and then exhale longer, as if you are letting dust settle, letting the day fall away grain by grain. Inhale again, soft and steady. And as you exhale, picture the blowout phase, not as turmoil but as release. The moment when a hidden core becomes unburdened, when what is trapped finds an opening and drifts outward, harmless, thinning into space. Let that be your body now, not fighting, not holding, simply letting go. With each exhale, imagine the dust around your thoughts becoming less dense, the sharp edges of concerns dissolving into a smooth haze, and through it, a calmer light emerges, not brighter, just clearer, like infrared vision quietly seeing through fog. In the distance, imagine a wide telescope floating above the atmosphere, listening, patient, catching faint whispers, and never judging how faint they are, because even the faintest signal matters, even the smallest breath matters. Let your breathing become your signal, a private transmission that says, I am safe, I can soften, I can drift. Inhale, and feel the body gently expand, as if you are a small universe inflating. Exhale, and feel gravity return you to the bed, not heavy, just certain, like a blanket that knows exactly where to fall. Let the idea of magnetic fields become a comfort, an unseen shield, a quiet boundary that holds what needs to be held, keeping the atmosphere of your own inner world from being stripped away by the wind of the day. Imagine Earth's magnetic field as a slow, luminous ribbon, invisible but real, arching over oceans and continents, and imagine that same kind of protection around you now, a gentle arc of calm, letting thoughts pass by without taking anything from you. If a thought arrives about the dark forest, let it fade into something softer, not hunters, not fear, just silence as a form of distance, a respectful space between things, like two ships on a dark sea passing without needing to speak. The cosmos does not demand that you stay awake to guard it. The cosmos has been carrying on for billions of years without your vigilance, and it will continue while you rest. Let the Big Bang questions loosen too. You do not have to know what came before. You do not have to build a multiverse in your head tonight. You only have to feel the simplest truth that you are here, in one small warm pocket of a vast reality, breathing in and out, and that is enough. Picture the universe as a slow tide. It expands in your imagination, then settles. Stars form, then quiet. Dust drifts, then gathers. Signals travel, then arrive. Everything moves, but nothing hurries. Let your eyelids follow that rule. Let them grow heavier without effort. Let your jaw unclench. Let your shoulders drop as if you are setting down a heavy telescope you have been holding all day. Let your hands rest like small moons in their orbits. Inhale and feel the breath fill the belly, then the ribs, then the upper chest, and exhale, longer, as if you are sending a gentle radio wave outward, low frequency, smooth, steady, a whisper that does not need an answer. In the darkness behind your closed eyes, let images rise and fade without grabbing them. A quasar core, a red dust veil, a jet like a thin stroke of light, the deep black of a galactic center, the soft glitter of distant stars, a quiet planet wrapped in an invisible shield, and far away a faint signal arriving after years of travel, not to alarm you, but to remind you that distance itself can be gentle. And now we arrive at the end of the night's journey, the place where the voice becomes softer, slower, where you do not need more information, only more ease. If you are still awake right now, still listening, still holding on to the last edge of consciousness, I invite you to do one small thing before sleep takes you. Leave a simple comment with your good night, or tell me which image stayed with you: the red quasars, the whispered signals, the invisible magnetic shields. And if you want to travel deeper into these cosmic stories, subscribe to the channel so we can meet again in another quiet night sky. And if you are already asleep, if your breathing has already slipped into its own slow orbit, then there is nothing more to do, no instruction to follow, only this wish drifting toward you like a warm, silent wave. May your dreams be gentle and bright in the way distant galaxies are bright, soft and far away. May your mind wander through calm starfields without fear, and may every unsettling question we touch tonight dissolve into wonder, the kind that does not keep you awake, the kind that rocks you deeper into rest, until morning arrives as quietly as starlight reaching Earth.